All right, let's dive right into this. Welcome to the Explainer. Today, we're taking a deep, fascinating look at the ultimate invisible architect of our digital lives, the operating system. You use one every single day, right? Whether you're tapping on a smartphone, typing away on a laptop, or even just starting a modern car. But most of us never really stop to think about the absolute mountain of work this software is doing completely behind the scenes. So today, we're pulling back the curtain. Think about the exact moment you press the power button on your device. What actually happens? Because for a split second, your computer is just a dumb collection of metal, silicon, and electricity waking up in total, utter chaos. It desperately needs a manager. Instantly, a tiny piece of firmware known as the Bootstrap program springs to life. Its sole purpose is to initialize the system, find the operating system's core, what we call the kernel, load it into memory, and basically just hand over the keys. It's the initial spark that brings order to all that chaos.
To really grasp the big picture here, it helps to think of your computer system like a massive manufacturing factory. Down at the very bottom, you have the hardware. That's your physical machinery, the CPU, the memory, the storage drives. Up at the very top, you have the users, the customers making requests. Just below the users are the application programs, things like your web browser or video games. Think of them as the specialized factory workers. But the operating system? The OS is the great intermediary. It's the factory manager. Without it, those specialized workers would have absolutely no idea how to safely or efficiently operate the heavy machinery.
So if we want to be strict about our definitions, an operating system is exactly that, a program acting as an intermediary, allocating resources and controlling execution. Now, to be fair, there is fiercely debated nuance here in the tech world. Some will argue an OS is everything a vendor ships in the box. But computer scientists generally agree on a much tighter definition. The OS is essentially the kernel. It's the one single program running at all times on your computer, constantly managing conflicting requests, making sure every single app gets its fair share of the CPU, and preventing catastrophic system-crashing errors. Okay, here's our roadmap for this explainer. We're going to cover the invisible digital manager, hardware interrupts and dual mode, the system calls step-by-step, operating system architecture types, real-world OS structures, and finally, the future of computing. Let's jump straight into Section 1, the invisible digital manager. We've established that the OS is the factory manager, the ultimate traffic cop of your machine. But what exactly are the services it provides? Well, the OS actually handles two very different buckets of services. The first bucket is all about you, the user. It provides the user interface, whether that's a graphical UI with clicking icons, a command line interface, or a touchscreen. It also handles file system manipulation so you can easily save and find your documents. But the second bucket of services, that's entirely hidden from you. That's about system efficiency. The OS is constantly allocating CPU cycles in the background so your music keeps playing smoothly while you browse the web. It's managing memory, and it's enforcing strict security protocols so a buggy app doesn't take down the whole machine.
Which brings us to our second section, hardware interrupts and dual mode. And this raises a really essential question. If the OS is running on the exact same hardware as all your sketchy downloaded apps, how does it protect itself?
The answer is a brilliant hardware-level division known as dual mode operation. Think of it kind of like a VIP club versus the public streets. When your standard applications are running, the CPU is in user mode. That's the public street. Apps can do basic things, run their calculations, hang out, but they're highly restricted. But when the OS needs to do something critical, like actually access the hard drive or allocate new memory, it switches to kernel mode. This is the highly restricted VIP club. And the craziest part? This isn't just a software rule. It's enforced by a physical hardware mode bit. Literally a 1 for user and a 0 for kernel. Privileged instructions simply will not execute unless that bit is a 0. So how does a standard app actually get anything done if it's locked out of the VIP club? Well, it has to politely ask the bouncer. It triggers what's called a system call, which acts as a software interrupt or a trap. The user process executes a call, the hardware safely flips that mode bit to 0, the kernel takes complete control, executes the privileged task, flips the bit back to 1, and finally returns control to the user app. It is a beautifully choreographed, highly secure handoff. And this ties into a really fascinating insight. Modern operating systems are entirely interrupt-driven. Left to its own devices, the OS kernel will just sit there completely idle. It only acts when an event absolutely demands its attention. Whether it's a hardware interrupt, like your keyboard sending a signal that you hit the spacebar, or a software error, like a program trying to divide by 0, the OS instantly pauses, preserves what the CPU is doing, jumps in to handle that specific interrupt, and then resumes normal operations. It's a lightning-fast, entirely reactive manager.
Let's move to Section 3, the system calls step-by-step. I've mentioned this system call concept a few times now, so let's actually slow down and unpack it.
Let's look at a task you do all the time, copying a file. It feels instantaneous to you, right? Just drag and drop. But behind the scenes, your application is triggering an intense marathon of system calls. First, it has to call the OS just to read the input from your screen. Then it calls the OS to open the source file. If the file is missing, another call to abort. Then a call to create a new output file. Then it enters a loop, trapping into kernel mode to read a tiny chunk of data, trapping again to write it to the new file over and over and over, until finally it calls the OS to close both files and terminate. This one seemingly simple user action is actually a massive sequence of privileged OS requests. Imagine if programmers had to write all those messy, direct system calls from scratch every single time. It would be a total nightmare. And that's exactly where APIs, or application programming interfaces, come in. Think of an API, like Win32 for Windows or POSIX for Mac, like a restaurant menu. The programmer just orders open file from the menu. The API then takes that order, automatically packages the necessary parameters, maybe dropping them in registers or pushing them onto memory stack, and hands it directly to the OS system call table. The massive complexity of the hardware is entirely hidden from the developer. Moving on to Section 4, Operating System Architecture Types. This gets into some fierce historical debates among computer scientists about how we should actually build these massive kernels.
See, there are fundamentally different philosophies here, and they come with massive trade-offs. The original Unix approach was monolithic. They essentially shoved everything, file management, CPU scheduling, memory management, into one giant kernel. The advantage? Blazing fast performance, because everything is already inside the VIP club. The downside? It becomes a massive, tangled web of code that is incredibly hard to maintain. To fix that, researchers created the microkernel structure, like Mach. They stripped the kernel down to the bare minimum and moved most services out to user space. This made it incredibly secure and reliable. But all that constant communication back and forth between user space and kernel space, it created a massive performance tax.
The sheer, mind-boggling complexity of OS architecture brings us to one of my all-time favorite insights in computer science, Kernighan's law. It states, debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are, by definition, not smart enough to debug it. This wonderfully counterintuitive idea is deeply, deeply true for operating systems. Because OS code is so incredibly difficult to untangle, developers have to rely heavily on automated crash dumps and trace listings just to figure out what on earth went wrong when a system freezes up.
Let's move on to Section 5, Real-World OS Structures, and see how this actually applies to the devices you're using right now.
The reality is, the fierce debate between monolithic and microkernels pretty much ended in a compromise. The modern world runs on hybrids. Take Linux, for example. It uses a highly performant monolithic core, but it's modular, meaning it can dynamically load in specific drivers only when needed without forcing you to reboot. Meanwhile, Apple's macOS is a true architectural hybrid. At its deepest, most fundamental core, it uses a Darwin environment, which actually contains parts of a Mach microkernel combined with BSD Unix, all sitting perfectly underneath its famous Aqua user interface. Now, scale that down to mobile devices. These massive structures had to adapt drastically to deal with strict battery limits and totally different usability constraints. Apple's iOS is heavily based on their proprietary macOS Darwin core, but it's specifically optimized for ARM processors and touch interfaces via Cocoa Touch. Google's Android, on the flip side, is built on top of the open-source Linux kernel. But Android modifies it heavily, adding super aggressive power management protocols and using specialized environments to run Java-based applications incredibly efficiently on phone hardware.
And finally, Section 6, the future of computing. Where is this invisible architect going next?
The traditional line between your personal, standalone computer and some distant server, it's completely blurring. We're moving into environments where peer-to-peer networks allow every single node to act as both a client and a server. We're seeing widespread virtualization, where an entire operating system is just running as an application inside another operating system. And that virtualization, it's the absolute foundation of cloud computing, where massive data centers deliver processing power and storage dynamically across the globe, all while tiny, hyper-focused, real-time operating systems are embedding themselves into everything from pacemakers to smart thermostats. Which leaves us with this final, thought-provoking question to chew on. As our computing environments evolve away from a physical box sitting on your desk and into virtualized, globally distributed clouds, what will the kernel of the future actually look like? Will it be a completely decentralized web of microservices? Or will one monolithic superkernel manage the entire cloud? Whatever form it takes, the operating system is going to remain the ultimate invisible manager, quietly bringing order to our digital chaos. Thanks for joining me on this explainer, and keep exploring.